Welcome. Thank you for joining. My name is Jaime Lopez, and today I'll walk you through how we can see some real-life impact from Flink use cases. And this is a pretty specific use case, and how we can actually literally keep the lights on, not just metaphorically. Energy systems power our daily life. Blackouts don't just cause inconvenience, they carry massive economic costs and sometimes even human costs. So this is why milliseconds matter. By way of background, I trained as an energy engineer, actually in Spain, later studied statistics, data science at MIT, and I spent the first 8-10 years of my career focused on energy. So forecasting solar production for solar power plants in Spain. We published in Technometrics in 2014 some advanced algorithms for day-ahead prediction. And then I went on to work on how to integrate variable renewables into energy markets in Southeast Asia, in the US, in Central America, in Spain, in Canarias, etc., etc. And today I do my other passion, which is marketing, at Reverica, the proud organizers of Flink Forward. So with this mix of technical market experience, I hope I can bring something interesting to our discussion today. And I'll start with a picture. You probably heard that on 28th of April of this year, the Iberian Peninsula, Spain and Portugal had a massive blackout. As I said, this is not just inconvenient. This is a system failure that touches hospitals, touches transport, touches communications, touches the daily life of 60 million people. And preventing this is the goal. I can share with you that I lived it up from, at the same time, very close and very far. I'm from Spain, but I live in Finland. My dad is responsible for a public nursing home in Spain with 120 people. When power went off, they were into absolute crisis mode. They had to keep these people healthy, alive, and feeling safe. And at the same time, they couldn't communicate with anything. Not even I could get a hold of them. So 28th of April, the cost of this blackout was estimated at about 400 million euros in lost consumption, lost GDP, basically. And unfortunately, this also costed some human lives. So 7 people died in Spain, 1 person died in Portugal due to the blackout and due to trying to mitigate the blackout, generator fumes, fires, etc. The goal is to prevent this. And I'm confident that the people we have here these days in Barcelona, we actually have the tools to make this less likely to happen. So this stems from a change in scale. As you see on the left, thermal plants, and on the right, renewable plants. Thermal plants do generate more emissions, whereas renewables generate little or zero emissions. Thermal plants, their fuel is costly. Renewables is free. But there's a catch, which is dispatchability. A thermal plant, basically a very large combustion engine, you can start it and stop it, you can ramp it up and down, more or less at will. Whereas with variable renewables, wind and solar, you cannot. It's the environment that decides how much power is produced. And these operate in 2 different time horizons. So if you think about renewables, the output will fluctuate in seconds, depending if a cloud passes over, or wind starts or stops, or blowing or changes direction. A thermal plant, yes, you can dispatch it, but getting started, a plant takes hours, literally. The fastest plant is between 45 minutes and 2 hours. A nuclear plant takes 3 days to start. So you have to balance this amazingly convenient dispatchability with very slow startups and amazingly convenient, free, clean energy with non-dispatchability. And I want to make it clear, renewables are not optional. They are a crucial part of our future as a species, and they're the backbone of that zero-carbon future. Since the 50s, we have multiplied by 4 our electricity use in humanity, and the carbon intensity, the grams of CO2 per kilowatt hour we produce, has gone down by half. And this is largely thanks to renewables. But there's the catch that we discussed. Every gigawatt of renewable capacity we add to the grid, it's a lot more volatility we add to the grid. And that volatility means risk. If you don't manage risk, it's cost, it means actually blackouts. So what makes energy unique? It's a commodity that up until very recently couldn't be stored or was very difficult and costly to store. So you have to match at every second the supply and the demand into the grid. When demand spikes, we wake up in the morning, you see it around like 6 a.m. This is yesterday's demand in the Spanish grid. People start turning out the coffee maker, people start turning out the lights. Demand starts to ramp up very quickly, especially work starts in large consumers of electricity, metallurgical plants, manufacturing plants, and suddenly you need to cater to that very quickly. And then at the end of the day, demand goes down, people go to bed, and you have to ramp down and take electricity away from the grid also very quickly. The markets, the grid is designed to manage this, but relies on forecasting and relies on agility. If your forecasting is off, you face a pretty impossible choice. You either curtail renewables and basically pull the plug, or you add instability to the grid and take a gamble that things are going to be fine. But both of those are pretty expensive. So wasting clean energy we don't want to do. Outages we also don't want to do. And this chart illustrates the biggest challenge with renewables. The green area, which is renewable production, has priority dispatch. You always want to put this first into the grid. Because of environment, yes. Because of cost, yes. But also because of law. In most countries, renewables have priority dispatch. And it's the first thing that gets fed into the grid. Which means that all the dispatchable sources have to adjust to fill this gap. And that gap can and will change size very quickly because of the demand curve, but also because this might just drop and suddenly you have no wind. So you constantly adjust output on these dispatchable plants to fill that gap between renewable generation and consumption. So to give you a sense of scale, a cloud over a solar farm can cut the output of that solar farm by 50% in 1 minute. That means that 50% has to be supplied somewhere else, somehow, by a gas turbine, by some other type of combustion plant. And you need to get the signal to the system to ramp up that plant before things go wrong. Too much renewable that generates needs curtailing, or too little forces like this scramble from dispatchable sources. It's a little bit of a nightmare. I have a good friend who works as a dispatcher, actually, and I don't envy his job. It's like being an air traffic controller with things that you cannot actually control. The way they monitor this and make decisions is by following voltage and frequency. Most of us here in the room probably have a technical background, engineering background, you know about complex numbers. So voltage is represented as a sinusoidal wave and with an amplitude and a frequency, and it's normally represented as a phasor in a complex plane. It's a complex number. When you see a change in amplitude of the voltage wave or a change in angle, that is the early warning sign that something is off. Either frequency is going up or down, or too much voltage, too little voltage. If you let this cascade, you might have a very big problem in your hands. And how do we make sure that we don't have problems in our hands? The backbone of the grid is controlled by and monitored by SCADAs. I think it was something like supervisory control and data acquisition systems. They're relatively old-fashioned, very robust systems that were put in the grid when these dispatchable plants were built. They're really good at most things. They are the ones that issue commands to PLCs that actually are going to action a switch, a voltage regulator, like can actually take physical actions. But they work on pretty low resolution time series data. They're built for the area where situations happen and develop in minutes or hours. So a SCADA polling cycle is somewhere between 1, 10, or 20 seconds, which means that you have one data point every 1, 10, or 20 seconds. Very good in the 80s, in the 90s, not enough for now. Why? We're going to see a couple of good graphical examples of why. If you see here on the chart on the right, like the definition of time resolution of a SCADA is going to be pretty low. And the way to combat this or to patch for it is to add something called Phasor Measurement Units. These are high resolutions, time series pieces of equipment that you add to a transformer, to a generator, and that can give you that high resolution time series data. They're going to give you 10 to 20 samples per second, so 10 to 20 hertz, which means that when in reality what you see in the PMU is the blue wave, what the SCADA sees is a much lower resolution signal, the red wave. That means that you lose responsiveness, you cannot act before your SCADA pulse again, and you also lose info. Like, you're never going to see this voltage peak in a SCADA, but you will see it in a PMU. And you install these PMUs to not just report the steady state condition, but this dynamic capacity of the grid to capture these events as they unfold. They are extremely useful to spot these oscillations, these drops, these sags, as they spread or before they spread. So, as I said, high resolution data, in contrast to SCADAs, you're going to be able to suddenly have real data with 50 to 100 milliseconds latency, which is 10, 20, 50 times faster than a SCADA can. You also get event timestamps from PMUs, which now starts to bring us into the event-driven programming and Flink world. You have to manage the order of those events. Obviously, in a time series, the order matters, and you also need to be able to guarantee that you process each event once and only once. If you do this well, you can actually add a whole layer of robustness and protection to the grid just by virtue of having better data. And where this matters a lot is in frequency. So this is a screenshot I took of the European TSO a few days ago, where they measured the frequency of the European grid at a couple of nodes. Frequency is the heartbeat of the grid. This is going to reflect the exact balance between generation and consumption. When you have more generation than you have consumption, frequency goes up. When you have more consumption than you have generation, frequency goes down. The set point, nominal set point in Europe, it's 50 hertz. In the US, in Americas, in some parts of Japan, it's 60 hertz. But here, 50. But every tiny deviation matters, and we are talking of very, very small maneuver bands, plus minus 0.1 hertz of nominal. If your frequency goes beyond these danger points that I wrote here, you start to have pretty bad stuff happen. The extreme example, most generators will decouple from the grid if your frequency is too high or too low. So you suddenly exacerbate the problem and have like a, let's say, vicious loop of cascading losses or additions to the grid. If we take the less extreme example, I don't know if any of you is based in Central Europe, but a funny thing that happened in 2018, there was a political dispute between Serbia and Kosovo, which caused one of the countries to say, like, we don't care about this. We're not going to do what the system tells us to do with frequency. So the frequency was slightly below 50 hertz for weeks in that node, and every grid-connected clock that measures time based on grid frequency started to sag. So ovens, microwaves, your alarm clock that you connect at home, at some point they were 6 minutes later than the actual time just because somebody was playing games with the frequency. Might be that you don't wake up at the time to get at work, but might also mean that your train is late because the schedule runs on a centrally managed clock. And if this gets too out of hand, you end up having an outage. Outages sound terrible, or a fault, but we're prepared for them. Faults are everywhere. Faults happen every day. When you're not watching, your TSO is managing faults because a cloud might pass over a solar farm, might drop the output by 50% and actually trip it, or wind, you get a sudden gust of wind and your generation goes like too high and also trips. A tree that falls onto a power line will also cause a fault. An inverter that fails, lightning striking something. It is an everyday matter. We know how to manage faults as long as we can detect them and as long as we can correct it and contain them. And containment relies on one and only one thing: speed. The costs of this delay in detecting, the costs of not acting with speed, will become clear very quickly. And in the end, sorry for the spoiler alert, but that's what happens, or that's what causes a massive blackout, like the one that Spain and Portugal suffered. So you get a fault that occurs suddenly. Your PMU is going to know about it in about 20 milliseconds, because the voltage is going to be high or low, the frequency is going to be high or low. The relay that controls that generation unit can also know it in less than 100 milliseconds, and will often do something. Will often like trip, disconnect from the grid, activate a protection, etc. But here we have the problem. Your SCADA is not going to know about it until 10 seconds later, if you're lucky. And because of our design limitations as humans, your operator is not going to know about it and be able to take action until 10 seconds later. 10 seconds sounds very fine, but we're going to see that it's actually not that fine. The day that the blackout happened, Spain lost 15 gigawatts of generation, which is about 70% of the capacity of that moment, in 5 seconds. This is what caused the blackout. If you catch this before these 5 seconds elapse, you would have avoided the blackout. And the big takeaway of this is that speed matters, speed kills or keeps you alive, and you can actually solve this purely by being fast. So blackouts are not this abstract engineering problem, they're not this act of God, they're actual national crisis, economic crisis, social crisis. They don't unfold over hours. The trigger is something that lasts less than 5 seconds. And they cascade very, very, very quickly, much faster than a SCADA can detect it, much faster than a human can react. That is why the title of my talk was Millisecond-Level Monitoring and Response Matters. It is essential. The cost of missing these 5 seconds was 13 hours of zero power, tens of millions of people without electricity. No transportation, no telecom, no card payments, no phone, no ATMs, all because of these 5 seconds. So going a bit deeper into this, what this shows is exactly like you can see in the timestamps, these 5 seconds of what like a node in the grid, which is in the southern of Spain, in Carmona, Sevilla, like suddenly the voltage does zoom and goes to basically zero. And a little bit before that, the frequency starts to show something going on. So, well, meanwhile, by the way, green line is a node in Central Europe, which was far away from this and probably had a better protection infrastructure. Barely saw any dip here. They saw some oscillation, some resonance, that's fine, it can be managed. But yeah, 5 seconds, you lose 60% of generation, frequency goes from 50 to below 40 hertz, means that everything that needs to run at 50 starts to disconnect from the grid to avoid damage, and you progressively lose more and more and more inverters, more and more generation. So being very kind of honest, there is no way this could have been avoided by a human. Only an automated system with enough speed can actually do something in those 5 seconds. No SCADA, no manual dispatch could have reacted in time. They literally did the best they humanly could. But we are here to find something that can be better than what a human can do. We're talking about phasors. So when you see how quickly these oscillations spread in the grid, you see that the phasors that are measured at different points in the grid suddenly start to go completely out of whack. The nominal frequency and voltage shows us a dot that has no vector attached to it. And this is what happened in Spain during those 5 seconds. Everything went haywire. Even though the outage happened around here, you can see that all over here, 1,000 kilometers away, things were going out of control already within those 5 seconds. These are chain reactions. And the only way to stop the chain reaction is to be very early at the beginning of it and stop it before it spreads. When we go back to this, we see that, hey, by the time that operation understood what's going on, it was too late. There's nothing they could do. No manual action, no SCADA. So the grid has to be able to react at this scale. And this is basically 1/10 of a human blink. A blink is 250 milliseconds. So in 1/10 of a human blink, I need to detect it, and half a human blink, I need to act on it. literally using a very abused phrase, blink it and it's gone. A little bit more context on what happened. You see that some things were already going amiss before, but Spain, despite its best efforts from the TSO and from operators, was not ready to act when it was needed in this time. And now we go to a solution. We at Verberica have thought about this, have thought how this can be actually helped, and we have a proposal. That proposal hinges on using high-resolution PMU data on the extreme left, fed it into an event bus at sub-millisecond latency written, or millisecond latency from the PMUs to a Kafka, for example. You can partition it by grid nodes so that you have kind of different partitions telling you how things are going in each area. And you're going to be able to guarantee, when it comes into our data platform, that exactly once semantics. You're going to be able to ensure that every event is in order, it's delivered exactly once, and you can perform the analysis that you need. What is that analysis? You can do complex event processing, either like set some basic rules for what might happen, for voltage sags, for angle jumps, and you can adjust those rules on the fly when the situation needs it. What you might need in the morning peak is different than the evening peak. What you might need in the winter might be very different than in the summer, because renewable generation is going to be very different. So with complex event processing, you can have a really good grip on how these events look and whether or not a fault is happening. You're also going to be able to use all this collection of grid parameters from each topic to do machine learning on them and to figure out what is the next pattern I need to implement that might warn me ahead of time of trouble. Okay, we've done everything we could to to prevent trouble and to predict trouble, but at some point we have to take action. So you also can have within our unified streaming data platform a simple job, a fault action function, a job that's going to tell the system what needs to happen now that a fault has been detected. And within this very small latency of 100 to 200 milliseconds, you can action this and send it to the automated control and alerting layer, which are physical devices that already exist in the grid. They're going to be breakers, they're going to be interrupters, they're going to be coolant pumps at thermal plants, and an energy management system API, and you're going to have those notifications very ready. But by the time that the notification fires, the action has already taken place. The problem is already prevented. Also, something that's very, very, very valuable to transmission system operators is monitoring and charting. All the charts I showed you today come directly from the open data from either the Spanish or European transmission system operator. That's how they build their capacity to respond to trouble. There's in every country also a national control center that keeps a good grip on what's going on in the grid because it's critical national infrastructure. And this also is connected typically to emergency services. If you have a blackout in a town, you do need to scramble firefighters. If you have lightning on a plant or a distribution tower, you need to scramble firefighters and police as well. So all of this can happen at the speed of PMUs, so tens of milliseconds, and before 1 second has elapsed, we're going to have to detect it, alert it, and monitor it. Which also allows us to go a little bit beyond. So we detected the fault, we handled it by actioning some predefined mitigation mechanisms, but you can also prevent it from spreading. Luckily, in the electrical world, everything is really, really well procedurized and codified. So all the PMUs use the same protocols, all the SCADAs use the same protocols, all the breakers and trippers use the same protocols, and it's fairly easy for them to communicate with each other. In some cases, for example, via Ethernet. You can issue a trip command to a breaker of a plant over Ethernet. So in these 250 milliseconds, you're already going to have your fault isolated, the power line that fell down or that went on fire is isolated from the grid. Nothing is connected to it so that the grid doesn't react to it. And you can, within a second, calculate how does the grid need to adjust to avoid this path that now doesn't work. Do I need to go through a different path, or do I need to activate something else? So in 1 second, you can have these alternate feeder paths computed, and you can be starting or stopping the generators that need to patch for this miss. If everything goes to hell, you can also start thinking about black start. In the end, the only way to come out of a blackout is to start some generation that doesn't need to be connected to the grid to start up. So this is also planned by the TSO. You can already issue a black start command so that, let's say, a town goes black. There's going to be a generator that's going to patch it up and bring it back online before that spreads to the neighboring town, neighboring province, neighboring country. So yeah, in order to conclude and leave you with some takeaways that hopefully you can think about, the first one is that renewables, they're definitely the future. They're here to stay. But volatility introduced by renewables is also very real. It's costly and it's dangerous. But we have mitigation mechanisms for it. Blackouts spread literally faster than the blink of an eye. They're too fast for manual, for batch, or for legacy systems. We can only tackle them effectively with real-time data in streaming. And with streaming, a streaming architecture and PMUs, we can detect and act in less than 50 milliseconds. Literally, not a single citizen will notice that something went wrong, but the TSO has already anticipated the problem and solved it before it becomes bigger. Us at Verberica believe that our unified streaming data platform can and will be a very good source of this reliability at scale. That's why we're working with energy operators in how to implement this to their operations. And all in all, if you have to remember one thing from the talk, is that real-time stream processing will literally keep your lights on. Thank you very much. We have a couple of minutes. Do we have any questions? Do we want to do some questions? Yes.
Hello, thank you for the talk. It was great. Just a question about sort of resiliency and how you can be more fault tolerant, especially with a very critical use case like this. So in terms of like Flink apps going down or something and having cross-regional, I guess, resiliency, like what kind of considerations go into something like this when it's that important of a use case?
It's a really good question. Flink in general, and most of the systems have been designed to live in a volatile environment and to not fail if one node, one broker goes down. So we can only use systems that are battle tested in less critical use cases, like IT, to apply them to this. I would always recommend to do like an N+1 configuration so that you always have something kind of in backup if your node, if your broker, if something goes down, that there is something ready to pick up that issue or that load. And I don't know if that answered the question or what else am I?
I think one of the other things I was also curious about is in terms of, I guess, operational deployments and stuff, because you don't want to have any gaps in terms of like a zero downtime in terms of deploying or going up or upgrading something like that. Is there any special considerations there, I guess, from an operational level as well?
It's a good question. Most of these things are designed to like 4, 5, 6 nines and above. Is that enough? In some cases, no. And I think it's something that has to be kind of mapped a bit case by case. But yeah, this is a system where literally no downtime is okay.
Awesome. Thank you.
Any other questions? All right. Thank you very much for coming.